Welcome to Lecture 23 in this series of modules on statistical quality assurance and statistical process improvement. This module concerns the simple statistical graphics for quality assurance. The context is this, that we've made our way through step 1 and 2 of this 6-step process-oriented quality assurance cycle of Vardaman and Jobe, and are to step 3, considering the habitual collection and summarization of process data. The previous module made some comments about qualitative principles of data collection, and in this module we're going to speak of some use of simple statistical graphics as in the context of quality assurance. So let's begin with the observation that that very simple things can sometimes be extremely effective. In particular, in every elementary statistics course ever taught, one is shown the idea of a histogram, and there are various kinds of nomenclature are provided for those histograms. What's important for application is how one interprets the shapes of histograms and their location and their spread. Here's an example of a bimodal histogram. So that's a piece of terminology that is often put forth in an elementary statistics course without any discussion of how such a thing might arise. In a quality assurance context, such a thing will often arise if there are two fundamentally different versions of some process element upstream from the place that data are being collected. One might have machine number 1 producing these values, machine number 2 producing those values, for example. That picture already begins to give one some ideas about what might be possible in the way of process improvement if one could take, say, the hump on the right and slide it to the left. One would decrease overall variation, and the interpretation of that would be getting rid of those fundamentally two different kinds of process, two different versions of a process element, and having only one version makes outcomes more consistent. More consistency in outcomes is essentially the guarantee of improved quality. If you take that idea to its extremes, people will even sometimes talk about doing single sourcing for parts, components that need to be very uniform. The idea is that if I have two suppliers, they can't possibly be doing exactly the same thing, and there will be more variation in parts that come from A and B than there would be from A alone or from B alone. It's common, as I say, in elementary statistics courses to invent terminologies for shapes of histograms. What's important is, though, is how those shapes get interpreted. Let me give you another example. Here's an example where what's portrayed are fill levels of some pop bottles that are to be filled to 591 milliliters in terms of a nominal fill level. So here's 591, here's 591 from machine number 1 and from machine number 2. What you see in this picture is that in both cases the fill levels are all above that 591, But in the second case, they're all above 591 with far less real variation than is seen in the bottles from process number 1, and it also looks like there's a bit of an odd shape here. It doesn't sort of go up and down like a bell-shaped distribution would go. It looks perhaps as if one had bottles that were filled according to this kind of a normal distribution, but there was some kind of sorting that has gone on. If that's the case, there's both more variation on the left than there is on the right, and there's also an implied waste or rework on the left coming from the sorting operation that perhaps was not as needed or needed at all from the machine that filled the bottles on the right. This figure already begins to illustrate an important point, and that is that marking engineering specifications on a histogram is often an effective way to communicate whether a process is currently meeting engineering requirements or whether it's even capable of meeting engineering requirements if one could somehow address the process mean. Here is a graphic that shows 4 kinds of cases. If I have a lower specification and an upper specification, the upper left picture is a portrayal of a situation where process output is consistent, will fit between those upper and lower specifications, and is properly aimed to do so. In the upper right, there are the same specifications. It's the same picture left and right. It's the same histogram in all 3 cases, but in the upper right, that histogram is not in the proper place to meet these lower and upper specifications. In the lower left, that histogram will not fit between those 2 engineering specifications or engineering requirements. And in the lower right, that histogram not only will not fit between those 2 specifications, but it's not even aimed appropriately. The jargon that is often used here is that for these 2 cases, the histogram is centered appropriately, while in the right 2 cases, it is not centered appropriately, so the process is not properly aimed. In the top 2 cases, the basic spread of the process distribution is small enough to fit between those specifications, so the process is capable, whereas on the bottom, the spread of the process or the spread of the output of the process is so large that despite wherever the mean is put, it will not fit between the 2 engineering requirements. So we can talk about properly aimed or improperly aimed, capable or not capable processes. Another kind of bar chart that has had a lot of popularity in quality assurance processes is the Pareto diagram. The idea is that one represents some measure of importance of different quality problems by bars of corresponding heights, measured the heights of those bars, measuring impact in terms of frequency of occurrence or dollar cost, and orders them from large impact to small impact, producing a picture about like this. So this is the most important problem that's faced. Here's the second most important problem that's faced. Here's the impact of the third most important problem faced. And if one makes cumulative versions of those fractions, one might add those might add that line graph on top. This is known as a Pareto chart. It is particularly useful as basically as a political tool to get people to focus on big problems first. In this context of bank audits for auto loans, the biggest problem that is faced in a check of loan files is that there's no current evidence of insurance. Well, that's something then that loan officers need to be aware of and really begin to insist on in their granting of auto loans. So another idea of another simple device of statistical graphics that's very effective, very simple, is the simple scatter plot. And it's a two-dimensional way of showing the relationship between a pair of variables. Those of you who've had a statistics course might well say, well, gee, I could compute sample correlation. Yes, that's true. But often a picture is more easily understood by non-quantitative people than the value of a correlation being 0.73. And so here is a pair of scatter plots. This is a count of type A defects. This is a count of type B defects on a series of items that have been inspected, or counts on lots of items that have been inspected. In the left-hand side, there seems to be some positive relationship between the counts of the two kinds of defects, whereas on the right there doesn't appear to be any trend or kind of apparent relationship between the two counts. Relationship suggests common cause. Not a guarantee of common cause, but if I was going to go try to do process improvement and I had a picture like the one on the left, I would ask myself, well, what kind of physical causes might produce both defects of type A and B, and those are the ones that I would go looking for first. The last idea that we want to talk about briefly in this module is the notion of plotting against time. That's a very important habit to get in as a quality analyst. Plots against time are very, very important in discovering change and causes of change and suggesting remedial measures. Here's a plot of 40 consecutive axle diameters produced on a particular lathe. Now, the first thing you might see here is that there is an upward trend in those axle diameters. The second thing you might notice is that as we go along here, the variation around that trend seems to get bigger. That's true to the way things work. As a cutting tool wears, if I'm pushing it in the same amount to a workpiece, the workpieces will tend to get larger with time, and they will also tend to be more variable with time, and that's the picture that's being shown here. Some kind of a automatic adjustment to the position of the tool might very well smooth this picture out or flatten this picture out, get rid of the upward trend, but it's unlikely that it would deal with the increased variability over time. The point here in all of this is that simple statistical graphics can be very informative about what's going on in a process and point one in directions of ideas for process improvement, and it's therefore a very important activity to make such simple plots, simple statistical graphics.